Hello, welcome to this training video where we will be modeling, analyzing and designing a composite filler beam deck type of bridge. This filler beam deck type which we will be seeing today is a skewed single span bridge which has got 15 steel eye girders encased in the slab. You can also see there are two parapet beams at the edges of this bridge. Now in this training we will be looking at two different types of modeling. One is the plate model which we are seeing now on the screen, where the slab will be modeled as plate elements, and we will extract forces and moments for rebars. And the other way of modeling is the grillage modeling, where the main girders will be modeled as composite sections, and then we will have some transverse beams for transferring the forces in the transverse direction. Both this type of modeling, we'll see how to apply different types of loads and how to generate the different transverse members. How do we generate the grillage model for different skew angles, and also we will see how the live load optimization is being done in the software. So let me first start with the plate modeling, where we will model the filler beams as beam elements or steel eye girders, and the slab will be modeled as continuous shell element or plate element type. So I'll be opening a new file. So I go to new project, and that's my new project window in MIDAS Civil. And first of all, I'll start by defining some materials and sections for the bridge that I'm going to model. So I go to properties and material properties, add. First I add a steel material which is S355 grade steel as per Eurocode, apply, and then a concrete material C40, and OK, and then I model the section that I'm going to use. So add, this will be an I section for the filler beams, so I type in a name, filler beam I section, and it's going to be a user defined section. So height will be 525 mm, it is 300 mm or 0.3 meters, 0.012 meters or 12 mm is the thickness of the web. Thickness of top flange is 35 mm. Width of the bottom flange is 400 mm, and thickness of the bottom flange is 40 mm. Now my supports for this bridge will be on the bottom flange, and so I have to change the reference line of this section from center or centroid of the section to the bottom flange of this section. So I will change it to center bottom, and I'll display the offset point so that you can see now that the bottom flange of this section represents the reference line. Okay, and apply. So one section is added. Now I will add the filler beam sections. So solid rectangle, the parapet beam sections. So one parapet beam will be the right side one, parapet beam right, so right parapet, and it will be 300 by 300 mm section, so 0.3 by 0.3, and this one will have a right bottom offset, and I'll just define a user offset. I'll explain to you later why I'm defining a user offset. So I just specify here 167, okay, and apply. Similarly, I choose a left parapet beam, this time with a left bottom offset. Click OK and OK. So I've defined 2 materials and 3 sections. Now I will define the thickness of the slab. So thickness, add, and the thickness of the slab will be 0.625 meters or 625 mm, and I will also give this an offset. So the offset for this will be minus 355 mm or minus 0.355, and click OK. Alright, so now I'll be starting with some node definition, and we'll generate some elements, and then we'll assign these properties to those elements. So I'll switch to the top view. X and Y are the horizontal axis, Z being the vertical, and the coordinate system follows the right hand rule. So first I will start by defining a point or a node. So node elements, create nodes, and just click apply. So a node will be created in the origin of the coordinate system. If you want to see the node number, you can always click on this button which shows N with a dot. You can see the node number here, node number 1. So similarly, if you generate an element, you can see the element number by clicking on display element numbers. Okay, I'll undisplay the node numbers, and now I'll generate a reference line for the skew. So create elements. I'll switch off the hidden view. This is used to see the rendered view, so for modeling I'll switch off this so that I can only see the line view, and then I'll switch on the hidden view later on, so we can verify if the rendered view is correct or not. Okay, so I just use the extrude element function. So element extrude elements, and just specify some material or section, and in the unequal distance we select Y. We want to create a line in the Y direction, which we will then rotate to create the skew reference. So I just type in the distances. So first point on this line will be 0.3 meters away from the origin. So 0.3 comma 14 at 0.6. 14 at 0.6 means there are 15 eye girders. They are spaced at 0.6 meter intervals, so therefore 14 at 0.6. so I'm just creating some nodes in the Y direction, from where I'll just drag the girders in the X direction to create them. So, and then comma 0.3. 0.3 meters is the distance of the parapet beam from the center line of the edge or the external eye girders. So just click apply. I just select the node and then click apply. Okay, so this reference line is generated. You can see the points, they are separated by the distance which I mentioned here. Now I will rotate this entire line to create the skew. So selecting all, this button is used to select all, and then going to rotate nodes and clicking on move. The angle of the skew is 15 degrees, and to measure it in the clockwise direction we write -15. Rotation axis about Z axis. First point, that is the reference point for rotation, is the origin. Click here and apply. So that's rotated the skew or the reference line. I close this, and we will extrude the slab and also the girders from this reference line. So just select all again, and we'll start with the eye girders first. So X direction, the total length of the bridge is 25 meters, so we will mesh it at 0.5 meter intervals. That's why I'll enter here 0.5 and times 50, so that will be 25 meters, and apply. So that generates all the filler beam eye girders. And now I'll generate some the slab elements or the plate elements. So I change this to line to plate, and again select the previously selected entities. This button is used to select previously selected entities, and type in the same 0.5 50 times. Thick type of slab, so this will consider shear deformation also. The element type is plate element, and I've selected source remove, which means this line will be deleted when the plates are meshed or the slab is meshed. And then I click apply, so that quickly generates the slab elements or the plate elements. I close this, and now we will assign the properties to the parapet beams. So just selecting the beam on the top, I'll just save this file as model 1, save. Okay, so I just select the exterior girders and assign them, one of them as right parapet beam and the other one as left parapet beam, and now display the rendered image. So click on hidden here. So now you see we have generated the skewed deck with parapet beams and also filler beams. I'll just check off the nodes so that it's more clear in the display. So this button is used to display or undisplay different entities. So just check off node and click OK, so it's more clear now. Okay, now if you see here, if I zoom in and switch off this hidden view, you see they're all in one line. So the offset which I gave earlier for the parapet beam has actually shifted the reference point, the center line of this section by that distance, keeping the reference line same. So the reference line is still the same, but the section has shifted upwards at the desired location because of the offset. The same thing happened for the slabs, the plate elements, and also for the eye girders. So now I have everything in one line. I can just directly assign some supports here. So I just switch to the top view and select by polygon. So this particular option, select by polygon, I can select these nodes. So there will be bearings below each filler beam. So just double click when you finish the polygon to select all the nodes. Repeat the same thing here. Okay, and now I go to boundary, define supports, and just say pinned. So dx divide is it all fixed, and rotation is free. So apply and close. So supports have been assigned. Now we will define some loads on this bridge. So we go to load. First we generate the static load case names. So starting with self weight, and just assign it a type, dead load, add. Similarly surfacing, say dead load again, add, and parapet, add. So let's say we have these three dead load cases to see in this for this bridge. Now we will assign some values to these load cases. So first, starting with the self weight of the bridge, so clicking on self weight and assigning -1, add, and this will calculate the self weight of the entire bridge for slab as well as for parapet and the pillar beams based upon the density and the section property of the different elements. -1 was entered here because the self weight direction is the gravity direction, which is in the downward direction or negative z direction. So I'll close this, and we will now assign some surfacing loads on the slab. So selecting pressure loads, select surfacing from the load case name, and I'll change the direction to global Z, that is vertical direction, and select the slab area which you want to specify for the surfacing load. So I just select an area like this, just create a window and assign a value in the P1 box. So -4, minus again because it's in the downward direction, and click apply. So that's surfacing load is applied. Now we will assign some parapet load. So selecting the parapet beams. Now you see that if you see on the works tree, you have two materials, S355 and C40. The C40 material is in blue color, which means concrete has not been assigned to any element. Anything which is in blue in the works tree represents non-assigned or unassigned elements or material properties. So we need to assign to the parapet beam and to the slabs the correct material property, that is concrete. So what I'll do is I'll just select the parapet beams by just pressing Ctrl and clicking on these two sections, and then once you select them, just right click and click select. So both the beams are highlighted, and now drag and drop C40 into the model view, and now if you double click on C40, you can see these two get highlighted. That means now the parapet has been assigned with the concrete material. Same thing we can do for our slabs. So just double click on thickness, which selects all the split elements, and drag and drop C40. That means all the plate elements and also the parapet beams have now been assigned with the concrete material. Okay, this was just to make sure the material has been assigned properly, because I missed it when I was defining the slabs, but you can very easily edit it. Okay, now I'll generate the parapet loads. So just select the exterior beams either by select by window or just control and click on the two properties and press select. Okay, now go to element beam loads and select parapet and enter -10 kilonewton per meter in the vertical direction. That will be the railing loads, and if there are any masonry wall on top of the parapet beam, we can enter the load of that on this beam. So click apply and the load gets added. Okay, so we have added the dead loads. Now we will add some live load on the bridge. So in this particular video we will be doing the Eurocode highway live loading, that is load model 1 and load model 3, and also the footway loads, that the pedestrian loads. So click on moving load and select Eurocode, selecting Eurocode. Now this bridge consists of plate elements. The slab is modeled as plate elements. That means the load distribution will be via the surface of the slab, which therefore we should use the lane type as a surface lane, not a line lane. Line lanes are used if you have grillage model, so you have only lines in the model and you use lines to create the lanes. But in this particular example we are doing plate model first, so for the plate model we'll take the surface lane. So traffic surface lanes, click on it, add, and we'll enter the lane for the first lane, which is footway lane, footway 1. The lane width is 1 meter, wheel spacing 1 meter. The distance, so we will be measuring the distance from this particular line, x equal to 0. We will be measuring the distance, so enter minus 0.9. The skew angle is 15 degrees at start and 15 degrees at the end, so 15 and 15. And now click on this first box in the 2 points selection window and click on the origin and click on the last point on the reference line, and then click apply. So that generates a footway lane. Now once you have done that, click again on this, press delete, so the previous information is deleted. Change this to lane 1, so this will be your notional lane 1. Change the lane width to 3 meters, wheel spacing to 2 meters, which is the general wheel spacing for the notional lane, and the offset distance, this should be the value of this should be 3 meters, so minus 3. Skew angle same. We can again click on the start and end points, or since we have the coordinates already saved here, 0 0 and 25 0 0, so we can just directly write add and click apply. So I'll just repeat again here, so delete this and just delete the previous lane. So I'll just show you again. So click on the 2 points, box 1, lane width 3 meters, offset distance minus 3. Click on the first point, click on the last point and click apply. That adds the lane 1. We just change it to lane 2 and lane width is 3, so offset distance just changing it to minus 6. Just delete it again, 0.1 to 0.2, apply, and then finally minus 8 meters, that is lane width 1 meter, wheel spacing 1 meter, and this is footway 2. Delete the previous information, again click on the first and the last point and click OK. So you can just display all the lanes by right clicking and display, and you can see that all the lanes have been added in the bridge. Undisplaying it, close, and now we will add some vehicles to run on this lane. So vehicles, add standard. This is a highway bridge, so we select the road bridge type of load model. If you click on this box, you can see that you can add road bridge, footway bridge load models, rail traffic load models like load model 71, SW0. So there are different types of load models for Eurocode, and the software has got a database of all the Eurocode load models. So if I click on road bridge load model 1, so I can add the adjustment factors. You can change them as per the national annex. So for example, like something like this, and click apply. Then we can add load model 3 vehicles. So load model 3 UK national annex, which can straddle between 2 lanes. So these are special vehicles or special order vehicles. So I just select SV80, just change the name to SV80, so that I can identify. Apply. And there will also be some pedestrian loads on the footways, so footway and footbridge, and click OK. So 3 load models have been added. If you have any unusual vehicle or any unusual load case which you want to consider in the live load optimization, you can just click on user define and you can change all these parameters. You can add your own load model 1 system, you can add your own load model 3 straddling vehicle, that is special vehicle. Just enter the axle load and the axle spacing, and you can consider the user defined vehicle for the analysis. Okay, I'll close this now, and we will now combine these load cases and tell the program to run the vehicles on such and such lanes. So moving load cases, add. The first load case is load model 1 plus footway, and just changing it to footway. Select all the lanes, select the footway lanes under footway category. We don't have any remaining area for this bridge, so we'll just leave it blank. Or if we had any remaining area, we first had to define the lane for the remaining area and just include that lane in this dialog box. So I'll click on apply. The second load case or load combination is LM3 or SV80 plus LM1. So LM1 plus 3, this is the load combination we will select. SV80. We can ignore the psi factor. This is a characteristic combination, so we can ignore it, and we can select both the lanes and bring them under straddling lanes category. So now the transverse position of the wheels will also change during the analysis, and the software will give you the worst possible position of the load model 3 vehicle for a particular force or deformation result. So click OK. So 2 load cases have been defined for the live load, and now we will define some control parameters for the live load analysis. So they come under the category of analysis moving load. If you click on analysis moving load, you can set some parameters for the analysis, like you can say if you want to calculate the normal plus concurrent forces, that is, if you want to see the combined forces, say the concurrent axial force in a beam when the bending moment is maximum. So if you check on this option, you can get those results. You can also set some calculation filters. So if you want to reduce the analysis time, you can say that I don't want to calculate for reactions. Say I don't want to check for displacements. The live loads I don't want to run for displacements. I want to run for reactions and forces. Or you can also say that you can create a group, structure group, new. Just right click and you can name it a result group. Okay, and you can say that say I select few members here and here, for example. Okay, and I just drag and drop. So I want to run the live load analysis and get the results for forces of these members, these elements. So I can just create a group, go to works tree, go back to moving load, and instead of all I say group, result group. So it will run and calculate the live load results for only these elements, so you can save time and focus on the critical areas in the bridge only. Click OK, and now you can just run the analysis. So analysis and perform analysis, and this will start the analysis for you. So I have already analyzed the model before, and I'll open it up now. Okay, so this is the analyzed model. Okay, so first, before checking the results, we can generate some load combinations. So results, load combination, and if I go to say the steel design, if I want to generate load combinations for the steel design, I can just write down a name, say ULS1. This is a strength type combination type add, so just add some description for your own reference, and then we can just select the load case, self weight, factor 1 say, and parapet surfacing, and say case LM1 plus footway. And we can also copy this, say click here and click and copy, so that creates another combination. So I name it ULS2 and say change this to LM1 plus SV special vehicle 80, and go to the next column. Or I can also auto generate. So if I click on auto generate and change to Eurocode, so based upon Eurocode it will generate some combinations. You can select road traffic and just mention which combination is under frequent or characteristic. So footway is frequent, click OK, and then click OK. So it generates few more combinations based on Eurocode, serviceability combinations. So these after generating these combinations, you can check the results. So first we'll start with reactions. We can select self weight and values, vertical reaction, apply. That gives us the bearing reactions for the bridge. You can extract it in a table format as well. So if I click here and click self weight, click OK, so it gives me the reaction at each with each node number and the summation of all the reactions, which you can cross verify with your self weight of the bridge to check if everything is fine with your model. Then we can also generate the displacement. So displacement contour, select say self weight again, check off values, check on legend and apply. So that is the displacement or deformation of the bridge. To see the deformation in mm, you can just change it to mm. Units can be changed at any time. That's 28 mm deformation. I'll change back to meters for checking the forces. So now we go to forces, beam diagrams, and select and apply. Just select solid fill, apply. So that gives the bending moment. This is the bending moment in the filler beams only. You can isolate the filler beams and check the moment. So what I'll do is I'll create another tree menu. So just right click and tree menu, works, and just right click on filler beams and say active. So that's only the filler beams in the view. You can see the maximum sagging moment is 178 kN/meter. Okay, we can also check the shear force, apply. Okay, and also the stresses can be checked. So the bottom flange stress in steel. So you can go to stress tab and say beam stress diagram, and number 4 is the bottom flange point. So combined stress or self weight, and apply, just change to solid, apply. So that gives the stress diagram of the bottom flange of the steel. You can change it to Newton per mm to get it in megapascal. Okay, so that's very low stresses in steel. So again shifting to kN/meter. Now the interesting part here will be the slab forces and how we obtain the slab design forces for rebar calculation. So for the slab forces, I'll just activate the slab. So just right click on plate and say active. So the slab is activated, and go to forces, plate forces or moments, and average nodal, say self weight, and apply. So that gives the bending in the x direction, or bending about y. This is the major axis bending, minor axis bending. Okay. So these are just bending moment per meter width of the slab. You can also extract a line diagram. So if I say cutting diagram, and say draw a line from this from this point to this point, add, and also a diagram from this point to this point, add, and apply. Just close this. You can see it gives me a bending moment diagram for MYY. Also I can get the result, sorry, it's plate forces, so I can also get the results for MXX. Cutting diagrams, add. So that's the variation of MXX. Now how to identify which is X and which is Y? This can be done from the display option. If I go to display and say element local axis and click OK, so that will take me to this type of a window where Z is the vertical direction, X is in the direction shown here for each plate, and Y is the direction of the bridge. So it should be for the major direction should be Y, so you should check for MYY to check the bending moment in the slab. And the transverse rebars can be calculated by taking the bending moment about MXX. Now we can also specify the angle of the rebar and get the reinforcement, get the moment in the top and bottom fiber of slab separately. So that feature is there in forces, plate forces moments, and we just change this to UCS, a user coordinate system, and say click on this box, this button, and say wood armor moment. Click on MYY, wood armor moment, and just specify the angle. So if it is, you want to place the rebar at 15 degrees from the y-axis, or which will be also 75 degrees from the x-axis. So I click OK and apply. So this is the rebar the moment distribution when you place the rebars at 75 degrees from the x-axis. So that is the moment along that particular direction in the top fiber. And if you want to get for bottom, just click bottom here, click OK, apply. That is the moment distribution. You can also get this in a table format. So result tables, plate forces, just going to result tables, plate force and stress, and just clicking on self weight, click OK. And plate UCS, that's where you will get the wood armor moment. So click OK, and now I click enter an angle here, say 75 degrees, and apply. So if I take the scroll bar here, and I can see M top, M bottom. That's the design moment for the slab, top and bottom, in kilonewton meter per meter. So you can actually calculate the rebars using these moments and place them in at a direction say 75 degrees with the global X. So that's how you can extract these slab moments from the analysis. Now the software also has the capability to do a steel section capacity check and also optimize the steel section. So I will just switch off the local axis and go to the demonstration for the section optimization. So click OK. Okay, so now I will click on initial view, so it will remove everything and bring me the initial view. Click on activate all to bring back the steel beams and also the parapet beams. And now I'll go to design, steel design, and make sure Eurocode is selected here, and just click on steel code check, so that will quickly read or check the steel members for the capacity check, and it comes up with a table. So this particular table, you can see that it starts with, it says OK, so the section is passing the check. The combined ratio is 0.884, so 88% of the section is being utilized. You can select this section and say graphic, so it will display a short preview of your section. You can also change this section, so if you are not satisfied with this section, you want a more economical section, or say you want to be more conservative, you can just say change and select any code, say BS standard, and select a section type and give your parameters here, if what type of depth you want, what flange thickness you want, width you want, and what type of combined ratio you want. So if I want a combined ratio between 0.8 to 1, and I search satisfy section, so the software will automatically search from the British standard and give you the list of sections which are satisfying this combined ratio for this particular structure. And you can just select one of them, say I select this one, or say this one which has a better utilization ratio of 95%. I say change and close, it will recheck, redesign, and come up with the steel code check again. Okay, so after the design, it says that it is failing the check, so that means the section is not good for the for this particular model. You can just say change again and search for another satisfied section, and say this time you go for this one, change and close. And this one passes a check. So you can also update this section. So if I click on update and bring it here, so it will delete all the analysis results and reanalyze the section now, new section, and will give you new design results. So that's the way of optimization in the software. If I just reset everything, so if I just go here and save section for design and reset all, so the previous sections will be retained. Okay, and then I can choose steel optimal design. The steel optimal design will allow me to select the section and give it say number of trials, 5 trials, and it will do a 5 times check and give you the comparative results for each trial, so that you can see how the section is being optimized. So it will compare the weight of the total model for each trial and give you the most optimized section after 5 trials. So that is also one way of optimization, which is followed in the software. You can use both these ways to get the most economically optimized section for steel. Now since we applied live loads on this bridge, we can also see the influence of the live load models on the bridge. So I'll go back to results and go to influence surface, beam forces or moments, and select a particular element. So if I want to see the influence surface for moment at the midspan, so I just select the midspan element, say 3D contour, apply. So you see the influence surface for live loads for this particular the moment at this particular element. Now to see the position of the vehicle causing the worst moment at this position, you can just go to moving load tracer, beam forces moments, and just select the vehicle load case LM1 plus footway or LM1 plus ASV80, and we just click apply. So that gives the vehicle position causing the worst moment. You can see the axle, the loads for the special vehicle. From the top view it looks more clearer. There is some straddling between lane 1 and lane 2. You can see this the difference here, that this is lane 2 and this is lane 1, and you can see the SV80 is somewhere in between lane 1 and lane 2, and this is the load model 1 axle with the UTL applied on the rest of the area. So it has only loaded the unfavorable spots in the bridge based upon the influence surface results. Now after this analysis, we will see the grillage model, how to do the grillage analysis for the same type of bridge, but this time we will take a skew angle more than the 20 degrees. The reason why I'm taking this is that when you increase the skew angle more than 20 degrees, the transverse element have to be kept orthogonal to the longitudinal elements. So we can't have the usual extrude option. Like in this case, you see the transverse direction members, they are actually the plate elements, they are all inclined with some angle which is equal to the skew angle. This is true for skew angles less than 20 degrees, which is in this case 15 degree. But if we increase the skew angle, we will have to make the transverse elements orthogonal to the longitudinal elements to get a more accurate representation of the deck behavior. So now what I'm going to do is model the bridge again, this time using skew angle of 30 degrees and also using composite beam elements with longitudinal girders and transverse girders modeled in the bridge. Okay, so I will switch to new project now. So file, new project. Okay, so I've opened up the new project now, and let's start with defining some lines and some grillage elements. So I'll start by defining a node, so like last time. So node elements, create nodes, and define a node at origin, apply. Now using this node I will create a reference line which will be my skew, which will be used for the skew bridge generation. So extrude, select all, and just define material section as it is, and node to line, unequal distance, y direction, say 0.3, 14 at 0.6, 0.3 again, and click apply, and select all the elements Close this, and I will rotate the nodes. So rotate, move about z-axis minus 30 degree this time, so orthogonal transverse elements will be used. Set and apply. So this is a very large skew angle, so select all, and now I will create the main girders, which includes filler beams and also the parapet beams. So extrude, and in the x direction 25 meters, and apply. Okay, so that's the main girders generated. Now for the transverse girders, I will again use the extrude option, but this time I will use the project option. So project, select all the nodes except the origin node, and select the baseline on which you want to project the transverse girder. So I select from this point to this point, that is the bottommost reference girder, and type in normal and apply. So this automatically generates some transverse girders orthogonal to the reference line. The same process I repeat on the other side. So select all these nodes except the node at the top, and just select the baseline by clicking on this point, and click apply. So that again creates the transverse girders orthogonally, and then copy these this transverse member, and we'll use the translate option. This translate option we will use, and we will use it to copy it along this direction. But before that, you can see here that this member has not been intersected properly at the longitudinal member locations, because you can see there is no node here. So we will use the intersect option to intersect all these elements. So I'll close this and select all, and go to intersect and apply. So now you see there are so many nodes generated at all intersection points, which is very important for the force transfer. Okay, so now we can just use them to use this transverse girder to copy in the longitudinal direction. So translate, and just measure the distance from this point to this point. Okay, says 20.5 meters. I'll divide it by 40 so that I have 40 intersection points, and copy it 39 times so I don't overwrite so that I don't copy on top of the girder on the other end. And make sure that you select intersect node and element, because we want the transverse member to intersect at each longitudinal member. Now click apply. So as soon as you hit apply, you can see it quickly generates so many transverse members for you. Just to check if they are intersected properly, generate the element numbers. So generate the element numbers, and you can see they are all individual elements. Okay, so which means that our modeling of the grillage is correct. Okay, so we have modeled the grillage members accurately. I'll just save it, model 2. The average transverse member spacing is 0.5 meters at the mid span, and at the ends it's half of that. We can measure it if you go to query nodes, you can just click on any 2 points, say this point and this point. It gives you 0.5 meters, and between this point and this point 0.3 meters. So roughly we can take the transverse girder spacing as 0.4 meters, and then we start assigning some materials and section properties. So we go to properties and go to material properties, add. So first we define a material for steel as 355, apply. Material for concrete slab, so C40, apply. Material for the composite section, so an SRC material. SRC is the composite material in civil, so composite, I just give it a name composite, and select S355 and C4050 and apply. And also I will have another section, another material property for the transverse beams, because the transverse beams I will assign them as concrete, but I won't consider the weight of the concrete for the transverse beams because I've included them already in my composite sections. So I will just select C40 from here so that the property is same, and change this to none. And once you change it to none, you can edit these material properties. So I make weight density as 0 and just rename this as transverse materials, so I can identify them later when I'm assigning them to transverse members. Click OK and close this. The next is section properties. Now for the composite section, which I'll open up the final model so you can have a look at the section type. The composite section should have individual rectangular section with steel encased in it. So we need to generate such a section manually. The best way to do is, if you have an AutoCAD file, you can create a diagram in AutoCAD, something like this, which has which clearly shows the rectangular box, a rectangular solid section with an opening here where your steel girder will come in, and the lines represent the center line of the steel web and steel flange, the lines inside this void. And then we will use this line diagram to generate composite section. So what I will do is I'll go back to the model which I was working upon and use tools section property calculator to calculate the properties out of that AutoCAD file. So tools section property calculator, I just use this units, click OK, and you can draw the same lines here also using different options which are similar to AutoCAD, like line, polyline, or arcs, etc. Or you can just import from AutoCAD DXF and just click on this file. Filler beam is the name of the DXF file which I saved, so it should be saved as AutoCAD DXF, and click OK. Yes, and you can find the same AutoCAD file which is imported here. Now what I'll do is I'll change the unit system slightly so that I have less difficulty adding the values here. So I'll change this to kilonewton and meter. Click OK and click yes. And now what I do is I'll assign materials to, I'll define some materials for concrete and for steel. So I click on material, add, and the first material is steel. Modulus velocity is 200,000 kilonewton per meter square. Poisson ratio is 0.3. Density of steel is 78 kilonewton per meter square. I click apply. Then click concrete. This time 35,000 kilonewton per meter square. 0.2 is the Poisson ratio. 25 density of concrete. Click OK, close, and now go to model, section, composite section, and generate a composite section. So generate, here we specify the number of parts our composite section has. So we can go up to 3 parts in MIDAS Civil. For this particular section we need only to have 2 parts, steel and concrete. So I just entered 2 here, just give a name composite. Base material which will be used for stiffness calculation will be steel, so I'll just click select steel and click apply. Close this and go again to model section, composite section, this time add part. So now we will assign material, so the software will know which material belongs to which line or which area in this particular geometry. So select part ID as 1, enter the name, say steel, part material is steel, select line option. Now before assigning the material, the software also needs to know what is the width of or thickness of the lines. So because these lines do not have any thickness for the steel web and steel flange, so I will just go to model, curve, and say change width, and go to alignment, make it center, width. Okay, and for simplicity I will change back my unit system to mm. So mm, click OK, yes. So I can write the thicknesses directly in mm. So type in 35. This is the top flange thickness, and select the lines representing the center lines representing the top flange. So press Ctrl, click on this line and keep the Ctrl pressed, and click again on this line and click apply. That assigns the thickness to the top flange. Now we'll change it to 12 mm for the web. So click on the web, apply, then change it to 40 mm for the bottom flange. So click on the bottom flange, Control, and click on the other outstand flange and click apply. So the thicknesses have been assigned. Now we go back to model section, composite section, add part, steel, part material is steel, line type is selected, and now just select these, click on the inside of these shaded area. So just select, Control, press Control and select the remaining ones. Make sure you select the area inside the steel, apply. So once you click apply, it will show some outlines here, which means the section properties for steel has been calculated. Now change it to part ID 2, concrete, and change the part type to plain and material to concrete. And now we will just select the outer lines. So select these, this line, keep on selecting. So just the outer lines, Control, okay. So the outer lines are selected, click apply, and it also gets shaded, which means the properties for concrete has been calculated. You can see the messages on the message window of the section property calculator. And now to calculate the properties, to display them in a table format, we go to calculate composite property, enter a mesh size. So our unit system was mm, so I enter a mesh size of say 50 mm, click on the any part, say steel, and apply. So it calculates the section properties, and to view them in a table format, click on composite property table. It shows you the properties for steel, for concrete, and for steel and concrete both combined. Close this, and now we will export this section to the main software, MIDAS Civil. So model section, composite section, export, click on any part and click on this box, give it a name, say filler beam filler beam 2, save and apply. That has been exported now. Close this, close the SPC file, you can say no, and now go to properties, section properties, add, and the composite tab, steel composite general. Okay, import from SPC, select the file which you just exported, open, click OK, and you can find the section properties listed here, part 1 and part 2. Okay, now we will change the offset of our main girders, the composite section, to center bottom like last time, because our supports are at the bottom fiber, center bottom. So you can see the point is shifted here, bottom. Click OK, apply. Oops, I'll add give a section name, so filler beam, click apply. Okay, now you can see as soon as I hit apply, all the elements have been assigned with section ID 1, which is filler beam. Repeat the same process for the parapet beams, which I did for my previous model. So I go to solid rectangle, say right parapet, user defined 0.3 by 0.3, and center, this is right bottom, and minus 0.65. Click OK, apply. Left parapet, this one is left bottom, click OK and apply. And then a final section property for transverse members. So we use the value property, because value tab, because in the value tab you can edit any section property irrespective of the shape. So if I say solid rectangle, and like I mentioned last time, the height, the width of the transverse members, the spacing of the transverse members is roughly 0.4 meters. So we can enter 0.4 here, and the height is should be the depth of the slab. So I just type in 0.625, 630, sorry, and just click on calculate section properties. So now it quickly generates the section properties for us. You can give it an offset similar to so that it is adjusted at the slab level. The reason why I used value type is because if I want to now change the section properties, I can change it. So if you have any voids in the transverse, if you want to reduce the stiffness in the transverse direction, you can do that by changing the area or the moment of inertia directly. So since in this particular example I'm not interested in extracting results for the transverse members, I just need them for force transfer, so I don't need to, I can only do with the work around with the section properties itself. I don't need the shape. So shape is usually used for the stress calculation. I don't need to calculate the stresses for the transverse direction, so I will just keep them as 0, 0. Just reduces the analysis time, and just go on with the calculate section properties, so that only the forces are transmitted. So just name it as transverse and click OK. So I'll now close this and check off the hidden or the rendered view, so I can just quickly assign the elements, their properties. So select the X direction members. So to select only the longitudinal members, you can change the selection filter to X and then click select all. So only the longitudinal direction beams are selected, and activate. So only these elements are activated. It's easy for selection now. So I change this back to none. Okay, and Now select the beams except the top and the bottommost beams, which are actually the parapet beams, and drag and drop filler beam. Okay, so double click on filler beam. Okay, sorry, I just need to assign them the exterior ones as parapet first. So select the exterior ones one by one. So the top one, that is the right parapet, bottom one, the left parapet. Okay, and then once I do that, I will I've already assigned filler beams to the to my interior girders, so I'll just double click on them to select and drag and drop composite. So composite material is assigned to them. Do the same thing for parapet. So click and control and click on the right and left parapet. Right click, select and drag and drop C40. So concrete will be assigned to them. Okay, so it seems longitudinal girders have been assigned with correct properties. We will now activate all the members. So activate all, and I don't need this inclined transverse girder. I only need the orthogonal ones, so I will delete that inclined transverse member. So I just use the polygon selection, select by polygon, and select just the transverse girder like this. Make sure, just zoom in and check if you have not selected the other girders. So only the transverse girders are selected. Now before pressing delete, just quickly remove all the nodes from selection. So you can see this is the node selection box. Node number 1 to 17 are selected. I don't want to delete the nodes, I want to delete only the elements, because if I delete the nodes, the other elements associated with these nodes will also be deleted. So what I do is I just select these nodes from the selection box here and press delete in the box. So when I press delete in the box, I am left with no node numbers inside it, and then press enter. So in the main view also you can see that only elements are selected, 1 to 16 elements are selected. Now click outside this box, like click here on the model view once you have clicked and press delete. That removes the transverse inclined members. I also don't need this projected part, so I just select it and delete. Also do the same thing for the other side. On this side I didn't model any transverse beam, but I have a projected member element here, so I just select it and delete. Now I need to assign correct transverse member properties. So what I do is I will right click on composite and say inactive, gone. So the main girders are gone. Then I right click on C40 and say inactive, parapet beams are gone. And now I select all and drag and drop transverse, select all and drag and drop transverse material. So that completes the modeling of this this bridge. I will activate all. So if I click on this button, everything is activated, and to check if they are assigned properly, switch on the hidden view. You can see that the properties have been correctly assigned. These are your filler beams, composite sections, okay, and the forces will be transferred in the transverse direction as well, because we provided transverse members. Okay, now we will start by assigning some loads and boundaries to the bridge. So again, switching back to the line view, checking off hidden, and use the polygon method of selection to create a polygon, just so that I can select all the nodes representing the supports. So just double click after finishing the polygon. Okay. Okay, and same thing here. Okay, selected, and now uh, we go to boundaries, define supports, and just say txt by dz rx and apply. So pinned supports are applied on the bridge. Okay, now we will assign some loads. So go to load, static load cases, and repeat the process self weight. This is a dead load. Add surfacing, dead load, add parapet, dead load, add. Close this, and this time we'll use self weight. Before assigning the weight, we will also do a composite construction stage analysis. So we will see the composite action taking place, the steel only stresses and the steel plus concrete stresses. So let me just create some groups. Groups are required for calling the loads or the elements at different stages. So we'll create groups, load groups. So right click on load group 1, new, and enter the load group name, so self weight. Right click, new, surfacing. Right click, new, parapet. We also need to create some structure groups. So if you don't have the tree menu on the right, you can always bring it by clicking on tree menu 2. So we will select the structure groups and assign the structure groups to the elements. So I will use the tree menu 2 for selecting. So you select all the composite beams by clicking on composite, and right click on structure group, new, and name it filler beams. Okay, and drag and drop, so all the filler beams will be included in this. Then right parapet and left parapet, just select them by pressing Ctrl, right click, select, and just create a new group, call this as parapet, and drag and drop parapet. Then select all the transverse members, so double click on transverse and just new, name this as cross beam. Okay, drag and drop, so cross beams group has been defined. And also for the supports, we select all the nodes in the bridge and just right click on boundary group and call it supports, and drag and drop the supports group and click OK. So all the supports are assigned and are included under this group. You can double click on supports to see the highlighted nodes where the supports were applied. Unselect all, go to works tree again. So we'll start by defining some self weight. Select load group as self weight, enter -1 like last time, add and close. Then we'll add some surfacing loads, so element beam load, surfacing, and say -10 kilonewton per meter. Now what we will do is we'll separate out the filler beams. So just right click on filler beams, say active, and select all the filler beams except the first and the last ones, the top and the bottom ones, and click apply. So filler beam, the surfacing load will be applied directly on the filler beam as a UDL. Okay, again active all, so click on this button, active all. This time parapet, change it to parapet, say -10 again. This is the parapet load, so select the parapet. You can select by creating a window or just uh, clicking and control click and select and click apply. Okay, just to check if we have divided the beams correctly, we'll do a check again. So display element numbers. Okay, there is a slight problem on this particular member. You can see that it's a continuous member number 81. So if I select 81, write down 81 here, press enter, it is a continuous member without any intersection. So we will intersect it. We'll use another feature for intersection this time. What we do is we will select all the nodes which are falling on this line, and we'll go to node element, say project, select move, select the baseline as this line, so this line is selected, and make sure intersect frame element is checked on and apply. So that should have intersected, the nodes should have intersected this element. Let's check. So if I click on display element numbers, now you can see there are some elements, new elements generated. 81 has shifted here, and you have new elements generated over here. So that's correct now. Okay, let's define the live loads now. So we'll go to load, moving load, select Eurocode. Now since this time we have a grid edge model, we'll not use the surface lane, we will be using the traffic line lanes, and we will be distributing the loads via cross beams. So traffic line lanes, add. The first lane, like the previous example, is footway 1, eccentricity is -0.8, wheel spacing 1 meter, cross beam type distribution, so select cross beam group here. Start angle is 30 degrees, end angle is 30 degrees for this skewed bridge. Selection by, click on the first and the last point for the on the bottommost girder and click apply. So that generates a footway lane. Change the lane name to lane 1, make it -0.28, -2.8. Wheel spacing 2 meters and 3 meters is the lane width. Delete the previous information, select again the first and the last point and click apply. So notional lane 1 is added, lane 2 -5.8. Again delete the previous information, first point and the last point, and apply. And then finally footway 2, and this time -8, 1 meter, delete everything and yes, and click OK. Footway 2 was not properly assigned. I'll just delete it and assign again. The eccentricity was not properly defined, so I will just name it again, footway 2, and give it an eccentricity -8, 1 meter by 1 meter. Just to make sure, I'll measure the distance. I'll press F4 and click on the 2 points. So it's roughly -7. So just type in -7. And cross beam type distribution. So cross beam 30 and 30 degrees. Start and end. Click. click, and click OK. So now this is properly defined. Close. We'll define some vehicles. So vehicles, add standard. Again, load model 1, you can define points, some adjustment factor 0.2. Click apply. Load model 3, this is SV80. Click apply. Footway, click OK. You can add some user defined vehicles if you have some unusual vehicles to analyze. So close this, and now we'll combine the load cases. So moving load cases, add. Load case name is LM1 plus footway. Footway, select all the lanes, footway lanes, and click apply. Then LM1 plus special vehicles SV80, LM1 plus 3 straddling SV80, and the straddling lanes are lane 1 and lane 2. Click OK. Close this, and now we will define some construction stages, and we'll specify at which stage the sections are steel only, and which stage the sections will be composite. So we start with load construction stage, define construction stage. So define construction stage, add name. So first is steel only. Only the filler beams are there in this stage. Filler beams, supports are there, and self weight will be there from the first day on this stage. So apply. Next step is the deck casted stage. So deck will be casted in this stage, and it will become composite. So cross beams will be activated. Boundaries, no need to activate any new boundaries. Loads, no need to activate any new load, because self weight will be considered for the slab automatically. Click apply, and then the next stage is construction of the parapet. So element, include the parapet load, apply. Then the next is deck surfacing. So no new element or no new boundary is added, only surfacing load will be added. Add, and just click OK. So that's 4 construction stages added. Now we will need to define at which construction stage the concrete becomes composite with the bridge, with the filler beams. So we use construction stage, composite section for construction stage, add, and just select the filler beam section. You can see automatically it will identify in the main model by highlighting the filler beams, the composite sections. Now we need to define some material. So material, the first part, which is steel, is S355. The stage in which steel is there, that is the first stage, steel only. The second material is part 2 material, which is C40 for the slab, and this is activated in deck caster stage. So this particular definition is very important, because the properties are varied based upon the stages in which you mention that which part will be activated. So click OK, close, and just like the previous case, we can change some parameters for analysis, like change the moving load parameters. We can run the entire model, say normal plus concurrent, okay, or we can run the analysis for a single element. Okay, so let's do the analysis for a single element for a moving load to make it a little fast. So I'll just select one element here and just say new result group, drag and drop. So only for this particular element the forces will be calculated. So I go back to moving load and say displacement check off, reactions check off, and want to see only the forces result, and normal plus concurrent force. So it will give you the concurrent axial forces or shear forces for maximum bending moment or any other force component, you can get the other concurrent forces as well. So click OK, and you can also set some parameters for the construction stage. Like if you click on construction stage, you can check on whether you want to include time effect, creep and shrinkage, and compressive strength effect. All those things you can check on. Just just check off include time effect and click OK for now. Okay, and once you've done that, perform the analysis. Okay, the model has been analyzed now, and we will now investigate the results for the construction stages. So I'll switch to stage 1, which is steel only, switch to the rendered view, and see the force results. So forces, beam diagrams, moment, and legend turned on. You can see that for construction stages we get results for dead loads, summation loads, and if we have the creep, shrinkage and tendon forces, we can also get them as separate load cases. And click apply. That's the bending moment diagram in steel girders. I'll change it to fixed format so the legend becomes more clear. Check off this. Now if you see, there the composite section forces are displayed part wise, part 1, part 2. Part 1 is steel, part 2 is concrete. So if I say part 1, this gives the same bending moment. If I say part 2, it gives 0 bending moment because there is no slab in steel only stage. Second stage, deck casted. See, now you can see some forces in the slab as well, part 2 and part 1. This is the steel and the total steel plus concrete in the composite section. That's the total bending moment. Similarly, we can do it for all stages. You can go to deck surface and see the maximum or the maximum bending moment, accumulated bending moment. Now another interesting feature is a stress feature. So you can see the stresses in different parts. So if I say beam stress diagram, if I have to see the stress in the top fiber of concrete, I can say part 1 and combined and 0.1 and say apply. That gives the stresses, the combined stresses in the top fiber of concrete. If I say sorry, this is steel, part 1 is steel, so part 2 top fiber of concrete, and if I say bottom fiber of concrete, part 4 combined and apply, that's the stress in the bottom fiber of concrete. Similarly steel, bottom flange, apply, that's the stress in the bottom flange of steel. Okay, so the composite section analysis actually enables you to extract forces directly for steel and the slabs. This is one big advantage as compared to the plate model, because plate model gives you forces per unit width, whereas the composite section gives you the absolute forces for the design in slab and also in the steel. Now another interesting thing is the moving load concurrent force feature. So if I go to result tables and beam forces, and we did the analysis for one particular element 1139, so I'll just check on that and check on this load case LM1 plus footway. For each element there are 5 parts in which the results are generated. I and J are the 2 ends of the element, and that there are 3 other quarter points for the result generation. So this on your screen you are seeing the result for the different parts of an element 1139, which is somewhere at around the mid span of the bridge for the load case LM1 plus footway. Now these are the maximum forces, maximum axial force, maximum moment. Now if I were to see the results for the concurrent forces, say what is the maximum, what is the moment value when axial force is maximum, what is the axial force value when moment is maximum. So I can just right click here, go to view by maximum value item, and say axial moment y, and click OK. Now this gives me the corresponding axial force when moment y is maximum. Again, so for example, this one, axial force equal to minus 143. When this is the minimum axial force, the most the maximum, you can say, compressive force in the beam, and the corresponding moment is 176. So it gives the concurrent forces for each and every component that you want to check for, so that you can get the combined bending plus shear plus axial force check and do the design. So the concurrent force feature is a really useful feature, and again, you can extract the worst position out of all your load cases from beam forces moment. I can say 1139 and click apply, and that gives the vehicle position for LM1 plus footway and LM1 plus SV80. That's the worst vehicle position. Okay, now we will move to the design feature, how to do the combined check for the composite section capacity check. So that can be done under the design tab, but before doing the design we need to generate some load combinations for design. So just like last time, we'll create some load combination from results load combination, steel design, and we'll say ULS1, say it's a strength type combination, and say it's self weight, surfacing or parapet, and say LM1 plus footway. Okay, I'll copy this, make it ULS2, change it to LM1 plus SV80, or I can just say auto generate Eurocode and SV80 plus footway is the frequent value, and click OK. It gives me some more load combinations. So I close this now, and I go to design, composite section design, enter some design parameters. So you can enter some parameters for concrete like 1.25, 1.15 for steel, 1.2 for structural steel. So different types of parameters you can enter as per Eurocode 4. Click OK, and you can also define some reinforcement material. So if I click here, you can click on the material composite and select the class of the rebar. Say class B rebar is being used for this analysis, this design. And what I'll do is I'll only display the composite beams so that it's more easy to select them. So I checked on initial view, and I right click on filler beam and say active, so only the composite beams will be displayed. And I'll check on the line view. Now composite design, we add longitudinal reinforcement in our sections. So click on longitudinal reinforcement, filler beam, and we can add the reinforcement now for the main rebar. So I'll give a guideline or clear cover. So it's 50 mm, for example, 0.05 for this section. Input method B. Click on the first point on the guideline, second point, number of rebars 4, and this is the 20 mm diameter rebar, so P20. H bar check on, and add, and repeat the same thing at the bottom, but this time we will use one rebar We'll shift this coordinate to minus 0.2 so that it's around this level, and click add, and do the same thing for the other side. This one, make it 0.2 here, okay, and add. So this is the effective this is the rebar configuration for one effective section. Click apply, the rebar gets added. I'll now close this, and now I'll go to the other tab known as define flange and web. So since this is a composite general section, we defined it from AutoCAD and then calculated the properties in section property calculator. So it does not have a flange and web information, it only has a property information. So for the design purpose, we need to know we need to tell the software which is flange and which is web. So choose define flange and web, click on pillar beam section, and click on this box. We have 3 group names already defined here. So, close this. So we need to define group name for each top flange, bottom flange, and for the web. So now we define select top, group type is top flange, and part name we give it a name, say part top 1, and select one of the outstand flange. Part type is outstand, add top 2, select this, add, then we change it to web, change the name, say web. This is an internal member, so internal, check this, add, then bottom 1, outstand, add, bottom 2, add. So we have added all the flange and web information. So I'll click apply, close, and then I can just select the positions where I want to design the sections. So design position, just select few of the sections here. So let's say I want to design for these many sections, okay, and click apply, and say I want to generate a detailed calculation report for one of the positions. So I say position for design output, and select just one section out of them, click apply and close, and then run the design. So once I click on design, it will start running the design for the sections, for the elements which I selected, for all possible subload combinations. So design is done now, and we can check the results from design result tables. Design result tables, bending resistance, click OK. You can see the bending resistance check, the elastic moment of resistance, the plastic moment of resistance, and what is the total moment of resistance. If anything is red in color, that means it's failing the check and you need to revise the section. And say if you want to see for vertical shear, you can check it for shear here. You can also print out a result. So print out a result in an Excel format, save as, give it a name, save. So it will start printing a result. Okay, so the detailed calculation sheet has been generated. You can see that bending resistance check, resistance to vertical shear, longitudinal shear for SLS checks. So all the different checks as per Eurocode, they have been they have been elaborated here step by step for you to refer to, and for also for report generation. So that's how the software does the composite section check, including reinforcement and slab and the steel. and you can get the result for bending resistance and also for the vertical shear. Okay, now we'll focus on the report generation. So we'll see what techniques are there for generating the reports. So I'll switch to the rendered view and say I want to take a snapshot of this bridge. I just say right click and dynamic report image and say isometric, click OK. That this image is saved. Now let's say if I want to take a snapshot of deformations, so I say displacement contour and deform, apply. That's the deformed shape of the bridge. Right click and say deformations, click OK. And if you want to take any table results, so table reactions, say for self weight, you want to if I want to arrange it in a sort them out based upon the vertical reaction, so sorting FZ and sort, so they are now sorted based upon the vertical reaction. Now I can just take a snapshot, say reaction table, click OK. And now I go to tools, close this, initial view, tools, dynamic report generator, new document. So you can also open an existing document with your own template with a company name and header footers, and you can use that to enter these images. So I go to reports tab and I can write in some text, say design report for filler beam deck analysis, and start copy pasting the images. So isometric, drag and drop, that's one image entered. Deformations, drag and drop, so that's another image in. And reaction tables, drag and drop, that's the reaction table entered. And then some section informations you can also enter, say the filler beam information. So the filler beam sections that is there in this that is used in this model, before composite and after composite. Also you can enter things like your static load cases, what static load cases you used, and also the bill of materials like weight, volume, surface area of each and every section. Then load combinations that you define in a model. So all these things you can use, and once you can save it, and if you want to modify anything in the model, you don't have to drag and drop again. You can just click on dynamic auto regeneration and it will come up with a box like this. You can select whichever images you want to update and it will update them in this report. So that's one time entry into the dynamic report. You can regenerate the report anytime you as many times you want to regenerate, and keep on modifying the model and generating the report. So that's it for the skewed type filler beam deck analysis. If you have any questions, please write to uksupport@midasuser.com. For information on other types of bridges, please follow or subscribe our YouTube page, MIDAS UK. You can get information about different types of bridges like composite steel, precast bridges, vibration analysis, and also pertaining to other fields like buildings and geotechnics. You can find videos on the MIDAS UK YouTube website. So that's it for now. Thank you. Bye.